14. We're going to call this part 2. Looking forward to it. There'll probably be 3 to 4 parts. It's a lot. I talk a lot. I want you to really understand this. So forgive me. Now, definitions, more definitions. Arteries carry blood away from the heart. Arterioles and capillaries. Arterioles are small arteries. Branches, small branches off arteries. Capillaries are even more branches, but this is where there's the site of exchange of oxygen, nutrients, wastes, etc. Then after capillaries, there's merging and returning of blood to heart. Once you exchange oxygen, nutrients, there's no reason for the blood to continue. You're going to have that blood return back to the heart to get reoxygenated. Now we're just calling them veins. Listen, it's a closed system. You have arteries, and you have arterioles, you got branching, you have exchanging with cells. Then you have merging, branching, merging, and bringing blood back to the heart. But it is a closed system. So these vessels are just named for which direction or what's going on with the blood, because all vessels originate from the aorta or the pulmonary trunk, and then they merge back to the heart. Pulmonary veins, superior and inferior vena cava. So closed system, get a handle on the definition of artery and veins. Arteries carry blood away from the heart, veins carry blood to the heart. And, whoops, sorry, I'm going crazy here. Nope. There we go. All right, so if you need to review your artery anatomy, it's the artery playlist, or the anatomy playlist on YouTube, chapter 22. This is taken straight from the anatomy playlist, chapter 22. This goes through the large arteries that conduct blood, and then those that are a little bit smaller branches off the conducting arteries are called distribution arteries. And here's where you see a lot of vasoconstriction, of decreasing the diameter and then decreasing blood flow, or vasodilation, where you increase the diameter and thus increase blood flow. And then you have arterioles that open up to capillary beds. So again, arteries are pressure reservoirs, those big arteries, because they are compliant. That means if there's an increase in blood volume, it's going to expand to kind of even out the pressure. So expanding pressure due to an increase in volume is going to be compliant, but it has an elastic recoil, which as the blood flows forward, that arterial wall can then elastic recoil back during diastole, and this keeps the blood flowing in one direction. That's part of that delta pressure difference. The pressure in the aorta is going to vary. When the heart is contracting, that is systolic blood pressure. You're going to have the maximum pressure. Why? Because myocardium or heart muscle is contracting, right? And that increases the pressure. Diastolic pressure, heart's chilling, myocardium is relaxed. And so it's just chilling. There's blood there, but it's not being pushed forward. Because arteries are elastic, they are considered pressure reservoirs because as blood surges and it expands that elastic component of the walls, the elastic component wants to snap back and keep pushing that blood forward. So because of that, we term them elastic. Veins are just compliant. Arteries are compliant, but only to a certain point. That elastic component is going to make it snap back. It complies and absorbs the increase in stroke volume, but then it's going to use its elastic component to go back to its original diameter. Veins are just compliant. They expand and then stay that way. So if you increase your blood volume, extra blood is just going to sit in the veins because they'll expand and just stay expanded. So they're just compliant. Arterioles are small. Remember, these have the largest impact on mean arterial pressure. They open up to capillary beds. And these are the vessels that are controlled by the nervous system and the endocrine system. So controlled by the autonomic nervous system and by the endocrine. So this is where hormones and the systemic or sympathetic and parasympathetic nervous systems control blood pressure. Again, the flow pressure relationship, if resistance goes up, by vasoconstriction, then there's going to be a decrease in blood flow to the tissue, and that can become a problem. Maybe not get enough oxygen due to a decrease in cardiac output or blood flow because you have a blocked artery. Blocked artery means that it's blocking blood flow through it. If you increase flow, make this purple or pink. Let's use pink because we like pink. This could be due to a decrease in pressure or vasodilate, decrease resistance. No, I did it wrong. Increase in pressure. We didn't want to put that. Looking at, I gotta stop saying looking at these. Here's low resistance, which means big diameter, right? This is big diameter. High resistance has a little diameter. Flow through the big diameter is going to be twice as fast as the low diameter. Why? Because it's going to take a longer time because the diameter is smaller, so fluid is going to move less at a time. So again, this idea of vasoconstriction and vasodilation, controlled by the smooth muscle in artery walls. And this is controlled by sympathetic and parasympathetic. Or we can just say autonomic nervous system. Vasoconstriction. If you increase the contraction of smooth muscle, what is that going to do? It's going to decrease the radius, which decreases flow and increases pressure. On the flip side, if we vasodilate, we decrease the amount of contraction of smooth muscle. And that relaxation, really, it's more of a relaxation of smooth muscle. It increases the radius, which is going to increase flow or decrease resistance, which will decrease blood pressure. However you want to think about it, because really it's all the same thing. So by controlling the smooth muscle, we're controlling minute to minute arterial pressure. So local factors that affect the resistance, i.e. blood vessel diameter, because blood vessel diameter is controlling resistance. And again, blood pressure, which is mean arterial pressure, is equal to cardiac output times resistance. So we're controlling resistance to control minute-to-minute blood pressure. So vascular resistance is regulated through changes in diameter. Is it vasoconstricting or vasodilating? If you increase diameter, you're going to increase blood flow. If you decrease diameter, you're going to decrease blood flow. So what local factors regulate vessel diameter? And looking at those, a couple of things. Nitrous oxide. Now, nitrous oxide is a paracrine, and it will be created by an adjacent cell to the smooth muscle. And when it's released, nitrous oxide causes vasodilation locally, meaning next door, meaning the vessel right in the area of the nitrous oxide. What else can do this locally? An increase in the partial pressure of carbon dioxide or a decrease in pH, meaning an increase in the concentration of protons. These will all cause vasodilation locally, not through the whole system, but just right where those are occurring. And so we call this autoregulation because nitrous oxide, partial pressure of carbon dioxide in that area, the tissue's not getting enough oxygen. It's using what oxygen it has to do Krebs cycle, which is producing carbon dioxide. Carbon dioxide is going up. Pyruvate is having to oxidize NAD and it's becoming lactate, which makes the pH go down. These are all local factors. And they are going to control the diameter of the local arterioles to that tissue area. Two reasons this happens. One is metabolic, meaning you're increasing the activity level of that tissue. If it's a muscle, you're using that muscle. If you are strictly riding a bike and you are not using your arms, you are creating metabolic activity in your legs. You are going to vasodilate the arteries going to those leg muscles. There's not going to be a high need to vasodilate the muscles going to your arms. So we have this metabolic system to control blood flow to areas that really need the increase in oxygen. There can be myogenic, which is you're stretching the arterial wall because there's too much pressure on it. Both of these factors, though, cause autoregulation. So we're going to look at these. This is really ultimately controlling, like I said, blood flow distribution. If you're not using your arms, you're not going to increase blood flow to your arms. If you're mostly using your legs, which is where you need that blood pressure. So changes with metabolic activity generally causes vasodilation. And what are those? An increase in the partial pressure of carbon dioxide It could be an increase in potassium in the area around the cell. Why? Because potassium is going out of the cell and not getting put back into the cell. Why? Because not enough active transport of the sodium potassium pump is occurring, and that can cause it as well. Or an increase in the concentration of protons, or we could say a decrease in the pH in that area. Why? Increase in lactate production, because we're doing anaerobic respiration. Changes with metabolic activity, and we're going to say changes with an increase in metabolic activity. Things that would cause vasoconstriction. And I was wrong here. This right here should be an increase in metabolic activity, and this is going to be a decrease. When you have a decrease in metabolic activity, you're not using the tissue as much. And if you're not using the tissue as much, you're going to have an increase in the partial pressure of oxygen because you're not using all of the oxygen available because you don't need it for cellular respiration as much because you don't need as much. No need for increase in ATP production. So you get an increase in the pressure of oxygen when you're not using it because you don't need to do as much cellular respiration as you were. And so this intrinsic control of blood pressure, if it's because of an increase in metabolic activity, we call it active hyperemia. It's an increase in blood flow due to an increase in the metabolic activity of a specific tissue, right? You are using that tissue and thus have a higher need for energy, i.e. ATP. You need more ATP. All comes down to cellular respiration, always does. So at a steady state, your oxygen that's being delivered is being used for cellular respiration. Of ATP production, and it's being produced at a rate it's being used. So ATP produced at rate it's being used. That is steady state. That is the definition of steady state right here. But when your metabolic rate goes up, why? Well, you need to produce more ATP. Because you need more energy to move actin myosin and calcium pumps and sodium potassium pumps because you're generating more action potentials. And so because of this, you need more ATP. Need more ATP. Well, how do we generate ATP? We're using oxygen as the electron acceptor at the end of the electron transfer chain, and during Krebs cycle, we're producing carbon dioxide. And so what is happening is the partial pressure of CO2 goes up, and if we can't produce ATP, if we're not getting enough oxygen, some of that pyruvate is having to convert to lactic acid to oxidize NAD. And so we're having a decrease in the pH. And so this is called active hyperemia. Oxygen is consumed faster than it's being delivered due to an increase in the demands for ATP. And CO2 is produced faster than it can be taken away. And so we have a drop in the partial pressure of oxygen and an increase in the partial pressure of carbon dioxide. That P, by the way, is partial pressure. I say partial pressure because air is a gas, which means it's a mixture. And that mixture is 20% oxygen and like, I don't even know, a couple percentage of carbon dioxide. There's not much. And then most of it, 80+% nitrogen. But we don't really use nitrogen. It's inert, doesn't really mix in with our physiology. So we just talk about oxygen and carbon dioxide, but they're a partial pressure, maybe 3%, something like that. I don't remember. But so we're just talking about that partial pressure that oxygen makes up in the gas. So I use partial pressure. We need to increase blood flow if we're using more oxygen. We need to deliver more oxygen, right? We need to increase delivery of oxygen to continue the electron transport chain and ATP production. So we need to deliver more oxygen. We need to get rid of that CO2. And those two factors are going to cause vasodilation in the area of metabolically active tissues. So that is active hyperemia. Reactive hyperemia is we get an increase in blood flow in response to a previous decrease in blood flow. Same thing happens though, you get an increase in metabolites, which might be a drop in pH, which is an increase in protons, and you'll have a decrease in the partial pressure of oxygen, and an increase in the partial pressure of carbon dioxide, and all these things cause vasodilation locally. But it's not due to active tissues. It's not due to you're using them for exercise or something. It's generally due to a blockage. So when you have a blocked blood vessel or artery, you're going to have a decrease of blood flow. And so you need to remove these things. And so when you see this right here between active hyperemia and reactive hyperemia, the difference here is active hyperemia, you're using the muscles or using tissues and need ATP due to increase in use, right? You need more ATP. They're active. Reactive hyperemia is you have a vessel blocked. And so there's just no oxygen being delivered downstream of that blockage. Both end up causing a decrease in the partial pressure of oxygen and an increase in the partial pressure of carbon dioxide. They both end up causing the same thing, but this is from a blocked vessel. This is from you're actually using it. But from here down, it's going to try to do the same stuff. It's going to try to vasodilate, decrease resistance, increase blood flow, so we can get more oxygen delivered and more CO2 removed, so we can restore normal amounts or normal partial pressures. That's local being intrinsic. extrinsic control of artery radius or diameter is really going to be due to the autonomic nervous system and endocrine. And again, mean arterial pressure or blood pressure is dependent on heart rate times stroke volume times total peripheral resistance. And this is controlled by these moment to moment. This is how we can control blood flow to different areas of our body. And so this is showing you cardiac output changes during exercise. Blood distribution is not proportionally delivered. You're going to have vasodilation to the muscles that are working, so you can increase blood flow. On the flip side, you're going to have constriction to vessels in areas where you don't need as much blood flow because they're not going to be active. And so you can see at rest, cardiac output of about 5 liters per minute. A large portion is going to your digestive tract and your kidneys because your kidneys are filtering blood. And then digestive tract is absorbing nutrients. From digested food, right? When you start to exercise, you're going to have active hyperemia. To the skeletal muscles, and they're all going to vasodilate. And so with that increase in cardiac output, most of the blood flow of that increase is going to the skeletal muscles because they are using a lot of ATP, thus they need a lot of oxygen being delivered. Gastrointestinal tract, you're not filtering your blood at this point. Those are going to vasoconstrict. Heart's getting about the same, or a little bit more, or I should say a lot more. Brain's getting about the same. Other areas, skin's going to have an increase because you might want to thermodiregulate. Thermodiregulate. You can tell I've been doing this too long, right? I'm just taping lecture after lecture. You think it's bad to listen. Try creating these. You just start rambling. Point is, blood flow is going to those areas that need more oxygen and being diverted from areas that don't need resources. How does it do that? Well, you can increase the firing. What does firing mean? Increase number of action potentials via the sympathetic neurons. And so you're going to increase blood flow. You know what? I'm just making stuff up at this point. Yeah. Let's go through this. So autonomic nervous system. Sympathetic control. So you have sympathetic autonomic innervation of the smooth muscle of the arterioles and of your heart muscle wall. So let's talk about the arterioles. Norepinephrine, that adrenergic neurohormone, binds to adrenergic receptors. That's going to cause an increase in constriction. It's going to cause vasoconstriction. It's going to increase mean arterial pressure, right? And vasoconstriction is going to cause an increase in total peripheral resistance. And so norepinephrine binds to the adrenergic receptors, binds to alpha and beta. If it binds to alpha, it's going to cause constriction. But on the flip side, epinephrine can bind to beta receptors, causing vasodilation. And so different adrenergic neurohormones are going to cause vasoconstriction and vasodilation. Do you have to memorize all this? No, but you need to realize that these are the autonomic uh, neurohormones that are controlling the vessel diameter, which controls blood pressure. So epinephrine, which is released from the adrenal medulla, again, can bind to alpha adrenergic and or beta. Thus, it can cause vasoconstriction or vasodilation. But norepinephrine can only bind to alpha, so it's always going to cause vasoconstriction. So here's where you get into that norepinephrine, epinephrine. There's 20% norepinephrine or 80% norepinephrine, 20%. This is when you get into the medicine of it, right? Nursing, physician's assistant, um, MD, DO, whatever. For your purposes, I'm introducing these ideas, and so you've heard it, and you go on, you can absorb more of it. Vasopressin, that's antidiuretic hormone produced by the hypothalamus and then released via the posterior pituitary. It's going to increase water reabsorption, which increases total blood volume in the cardiovascular system. More volume in a closed system can increase the mean arterial pressure. So that's one thing. This is long term. If you have more volume in a closed system, it's going to be more pressure in that closed system. If you have less volume in that closed system, it's going to be less pressure. That's why people that hemorrhage too much blood now have such a low volume that their blood pressure drops. And thus they don't have enough blood in the system to keep the pressure high enough to get it back up to the heart. That's a separate thing. Vasopressin or antidiuretic hormone also causes vasoconstriction, which increases resistance, which can also increase mean arterial pressure. Angiotensin 2 from adrenal medulla. I'm sorry, adrenal cortex. This is from adrenal medulla. Also causes vasoconstriction. Decreases the diameter, increasing resistance, which can increase mean arterial pressure, right? It's increasing the total peripheral resistance. So all of these factors are going to affect blood pressure or mean arterial pressure. All right, we're ending it here. Next.